Okay, for that question, if you read the question, it is about the n equal 0.5, n equal 1, n equal 2. So I spared that solution for the next chapter because we need to go through a few fundamental idea first to solve that problem. So I hope you could ignore the question about the n of 0.5 and so on. Okay, is that okay? Sampai situ boleh ke?
Yeah, it's okay.
Okay.
Boleh, Doktor.
Okay. So this is tutorial 16. So this is actually the new idea because the idea of no slip condition is actually the common one. We learned that in fluid mechanics in undergraduate, and then we always use that in master level because no slip condition is a real situation. However, now in this question, we are using the idea of slip velocity. So slip velocity means the molecule is actually not stick very hard. It might be 70% stick, but it still could move at certain speed. Okay, why this important? Because why this is important? It is because that in master level, sometimes you are doing something new. The idea of this one can be used when you do research about the nanoparticle, for example. If you coating your surface with nanoparticle and so on, maybe the dirt is not easy to stick on the surface. So when the dirt is not stick very well on the surface, so means that the dirt is actually do not it's not apply the idea of no slip condition. It's actually slip on the surface. So this is the idea. And sometimes if you do some modification in aerofoil to get, because in chapter 4, 5, and 6, we will learn about the boundary layer. So we have a few tricks to reduce the boundary layer to increase the lift force, for example. That idea will come along with the idea of the slip condition like this. If you use the idea of slip condition, you do that some physical modification of your aerofoil, so you could play around. You could delay you could prolong the boundary layer. You could prolong the separation point, for example, and then you need to take account of the idea of slip velocity. But the basic idea is like this. Okay, for example, repeat the analysis of the velocity profile between two plates in figure 1.15 for a Newtonian fluid, but allow for a slip velocity delta U at both walls. Compute the shear stress at both walls. The slip velocity can be written as this one. So this is the common equation for the slip velocity. So we assume that the del U can be assumed as L du dy, which is the L is the mean free path of the fluid. So the idea of dl is actually the movement of the fluid at that slip velocity actually. So and then this is the equation, and then the shear stress at upper wall is tau mu v over h plus 2l. So it is given in the question. So let's use this one. Okay, and then if you want to draw a velocity profile, so how you could draw a velocity profile with slip velocity. So for no slip velocity, so the velocity is stick very hard on this surface. So and then because this velocity also stick very hard on the surface, but it's moved along the surface, it's moved because the surface is moving. So it could create a velocity distribution like this. Okay, so well, you could draw the velocity profile is like this. So what happens if both of these molecule have slip velocity? So the idea is the simple one is at the bottom here. So means that because it's not stick very hard, so it could move at certain velocity. Then you could draw an arrow here to show that the molecule is actually moving at certain speed. So at this point, you need to think about the idea of relative velocity, because we have two velocities in that situation. One is the velocity of the moving plate, okay, and another one is the velocity of the moving molecules. So in physics, if you have two molecules move in the same direction, for example, so the total velocity will become lower. So because the effective velocity is actually about this distance. So I hope you could understand the idea of relative velocity. Okay, because it move, there are two moving things. One is plate and one is molecule. Both of them is moving at the same direction, so the total velocity will reduce. So means that if the no slip condition has velocity like that, so means that at the bottom here, so you could draw it start from this one, but at the top plate here, so the velocity actually is reduced a little bit, because you know the idea is the molecule is not stick very well. So when you push this plate at certain velocity, so this molecule maybe cannot follow that velocity. It will move, but it slip a little bit. So means it will move at slower velocity. That's why when you draw a velocity profile for slip condition, so it will become like that. Means you need to add an extra velocity at the bottom here, but at the moving plate, actually the velocity is reduced. So because this is the velocity of slip velocity. So I hope you could imagine. Okay. So and then we assume that the velocity profile is linear. So the assumption here is actually we could take from the previous calculation. So because the pattern of the velocity gradient here is linear, so we could assume that it is the value, the common equation is linear, which is a plus by. So and then we put the boundary condition. Okay, at the bottom, okay, we found that we have an extra velocity. So we have the u at the bottom. U bottom here is equal 0 plus delta u. Okay, the velocity is not 0 because there is slip on the bottom plate. So and then at the top velocity there, we found that the velocity is reduced a little bit because there is a slip. So we write down the equation as capital U minus delta U. So the capital U here can be replaced with the capital V. So we have two plates here. So this plate is moving at V velocity. So at this situation, V is equal to U. So it is okay. So the important one is you know how to modify your previous answer about the boundary condition to fit with the slip condition situation. So and then what we do is we do this calculation. So means that at y equal to 0, mean at the bottom one. So we have the uy at y equal to 0 and du at equal to 0. So we have the a plus by at y equal to 0 is equal to the L du dy at y equal to 0. So and then we substitute the value of y equal to 0. So we have a plus b 0. So we have an a. So and then here, so we know that, okay, from where this come from. So here du dy. Okay, we have a du dy here. We could write as d dy for u. So and then u here is the previous calculation that we get here. So we substitute the a plus by at y equal to 0. So means that the value of y equal to, okay, so we have first we need to differentiate it first. So you have ay plus by square over 2. So and then we substitute the value of y equal to 0, and then we could get it is equal to lb y square. Okay, I hope you could get this. So the value here is, so we have an a here, so we could get an b here, dy. So okay, so it is not integral. I'm sorry. So if you different this one, so a will disappear and by will become b. So mean there is no amount of y equal to 0. So then you will get a is equal to lb. So and then for the top plate, which is y equal to h, so we do the same things here, but we use the idea of velocity at the top, so which is u minus du. So and then we do the a plus by, which is the common velocity profile for the uy there. So the condition is y equal to h, and then we do this one. So and then u minus l du dy. So and then we substitute the value again. So and then we could solve this one by differentiate these terms, and then we substitute the value of h. So and then we get this one, and then we arrange this one, we could get the value of b. So and then the value of b here is substitute into the previous equation, so which is this one. So and then we have these terms, and then we could get the value of b and the value of a, and then we could substitute into the final equation of this one, a plus by, and finally you will get it is equal u in bracket l plus y over 2l plus h. So and then the shear stress. Okay, the shear stress, this is the common shear stress that I think you still remember when you do your undergraduate study. So tau is equal mu du dy. So and then the word du dy here is actually the differential of this one. Okay, so we already have the equation of uy, the function of uy. So we do the differential process here. So we get this value, and then we could say it is equal tau shear stress. Tau is equal mu u over 2l plus h. So if the h is equal to 0, mean the bottom. So the shear stress at bottom is this one, and the shear stress at the top is equal to mu u over ul plus h.